Hi everyone, my name is Dhruv Batra, and today I want to talk to you about this particular question. How far can we scale model-free reinforcement learning for embodied AI? It's a longish question, so let me unpack that into pieces, specifically starting with embodied AI. I am particularly interested in the transition from what you might call internet AI to what I would call embodied AI. By internet AI, I mean standard supervised learning paradigm applied to large static data sets typically gathered from the web, hence the term internet AI, to embodied AI, which refers to agent embodied in an environment, gathering information, taking actions, following instructions. And roughly, I think of these as two broad categories. Robots, which a lot of you folks might be working in, that is physical agents taking actions in the world, talking to humans in natural language, such as following instructions, go there and look for people, and so on. But there's also a second category, which is virtual assistants. That is virtual agents sitting on maybe smart glasses, taking virtual actions, but still talking to humans in natural language, answering questions like, where did I leave my keys? Okay, and if there's an AR display, show me the recipe for making guacamole, and so on. Both these types of problems have a common consideration, which is that there is an embodiment. There is an agent that is actually embodied in an environment and can therefore only be present at one time, has to take actions in a sequential manner, and follow grounded instructions. Consequently, there is also a common set of problems. In many cases, the hardware either doesn't exist or is too slow. The real world runs no faster than real time. The hardware or the experiments may be dangerous, both for the environment, for other participants, and for the agent. The entire setup might be too expensive and not easy to reproduce. In fact, that has been one of the main scientific concerns about a lot of these problems, that sometimes these experiments are not reproducible across labs at universities or sometimes even within the same lab. And the theme that we're going to explore is a common solution of SimtoReal transfer, which is that we train these embodied agents in simulation and before deploying them to realistic environments, either on robots or on other hardware devices. And this gets around a lot of the concerns that we talked about. This approach is promising in that simulations can run significantly faster than real time, they're safe, they're easy to reproduce, and they can be massively parallelized. And for the last couple of years or so, together with a broad set of collaborators, I've been working on this multi-institution, multi-year project, if you will, that was presented at CVPR 2 years ago called Habitat. It consists of a fast photorealistic 3D simulator that has the ability to render trajectories and simulate agents in environments as you see on the screen. These are datasets from Matterport 3D scans, Replica, which is a dataset of 3D scans of indoor environments released by Facebook Reality Labs, and a number of other assets. Essentially, the simulator has the capability to load in any arbitrary 3D space that has been scanned and create virtual replicas of them and render out experiences for an embodied agent. Habitat also consists of a library called Habitat API, which allows you to easily define virtual robot configurations, a number of tasks and baselines from imitation learning, reinforcement learning, and classical baselines from robotics. These are tasks of the kind object goal navigation, where you have a virtual robot spawned in an environment and given the name of a category, like go to sofa, and it has to navigate to an instance of that category. Or this could be a room navigation task, where you're given the name of an area in the house, like go to kitchen, or it could be instruction following, turn around, go out the bathroom, turn right, go out the brown door. So it's a long sequence. Or it could be a question. This is embodied question answering, what color is the TV stand? Dark blue. And the agent has to first gather evidence and then answer that question. Today, what we're going to focus on is going to be a specific embodied AI task. In particular, it's the task of embodied visual navigation, and more specifically, point code navigation. And by that, what I mean is this task is fairly easy to state. There is a embodied agent spawned randomly in a new virtual environment. And the agent is given goal coordinates of a position where it is asked to navigate to. So think of it as go 5 meters north, 10 meters west of your current position. The top-down map that we are seeing is not available to the agent. The agent must proceed and act from an egocentric perspective. This is only for visualization. All that the agent sees is egocentric depth. So the agent has a depth camera, egocentric RGB, and the agent is equipped with localization sensors, such as maybe derived from GPS or compass, that allow it to calculate where the goal is at every point of time. And these are all that the sensors that the agent has access to. So this is what a trajectory, an example trajectory would look like. The agent navigates, finds a place, calls stop. Now, if you're a robotics person, the classical robotics pipeline solution for this is you break this problem down into its constituents. There's a natural breakdown into mapping, localization, and planning, with decades of work in robotics on each of these problems. There's a key fundamental data structure, which is you build a map. The map can store either free space or semantics as appropriate for the task. You have to localize the robot with respect to the map. And finally, when you have this map built, you can plan a path towards the goal. This is the classical robotics pipeline. And in some sense, this is highly reminiscent of pipeline-based architectures in a number of other domains in AI. For example, phrase-based machine translation, where this used to be the paradigm in machine translation. If you had to translate from English to French, the way this used to be done is that you broke a sentence into phrases, constructed a phrase lookup table or a dictionary that converted chunks or segments of a sentence from one language to another, and then you learned how to put them together or decode them in the correct order, because different languages may not have the same ordering. As you may already gather from my connection to machine translation, we are going to take an entirely model-free approach to this. We're going to ask the question, just how far can you get on this task without any understanding of the task, without building a map, without doing any localization in that map, without doing any planning. So we're going to operate in an entirely model-free regime. And to be clear, I'm not claiming that is the right way to solve this problem. I'm just asking the scientific question, how far can you get with this approach? And so the approach that we're going to follow is we have an agent. It receives at every point of time an RGB image and a depth image, and a localization sensor that tells it where the goal is with respect to its current position. And what we're going to do is we're going to do standard classical computer vision, where we're just going to embed the image with a convolutional neural network and feed both the embedded perception and the goal into an LSTM policy network that is going to output both an action to take at the current time, like turn left, and a value function estimate of how well the agent thinks the current state is. This is going to be a recurrent policy, so the policy will maintain a notion of state or history and produce a sequence of actions: turn left, move forward, turn left again. And you notice that this is classical CNNs and LSTMs, and the only place where navigation comes in is a definition of the reward. We're going to give the agent a reward of some constant value S if a goal is reached, and we're going to give it reward shaping in terms of progress towards goal at all other times. This is the only place where the model architecture interfaces with the task of navigation. And we're going to train this entirely from scratch with no understanding of perception, with no understanding of navigation. All neural networks are trained from scratch. So with that set up, let's ask the question, how do we scale this? Because we know we're going to need lots of training data to solve this problem. There are two ways we're going to approach scaling. First, we notice that there is a perception action loop going on. Every time the agent takes an action, the simulator responds with a new observation, which is an image or a localization sensor or a depth sensor. So the faster we can get this loop going, the more amounts of training we'll be able to do. So it's going to be essential that the simulator runs extremely quickly. And this is exactly where it is worth making a point that there is a clear difference between game engines, which is what most AI simulators tend to be based on. That's how we might approach the problem of constructing AI simulators. After all, game industries have been working on this problem for a long time, and machine needs for AI. Now, human gaming needs are a specific point in the design spectrum. What humans need are high fidelity RGB images at roughly 30 to 60 frames per second or hertz. Anything faster than that, and humans are not going to notice any difference. And humans will just be consuming an RGB frame, not a depth frame, because that's not the modality preferred by humans or any other source of information. Machines, on the other hand, for AI needs, are going to be consuming an entirely different type of input. First of all, high fidelity RGB, high frame rate, high pixel resolution is not essential for AI. Where these things are just going to be fed into a CNN, and 256 by 256 is going to be fine for our purposes. What we do, however, care about is extremely high frame rate, because this is connected to the perception action. We're going to want upwards of 1,000 frames per second, maybe even 10,000 frames per second in these simulators. And we're not going to run a single instance of this because we don't just have a single monitor. We're going to run these distributed, headless on a cluster, and we're going to not ask just for RGB, but depth sensing, surface normals, semantic segmentations, localization, radar type sensors. You can imagine the entire suite of things that we would want to render out. And that makes it very clear why the design space of building a simulator for AI needs is very different from the design space of building simulators for human consumptions or game engines. So over the past couple of years, as I had mentioned, we've been working on this simulator called Habitat-Sim. Before us, there were a number of efforts that roughly lived in the 100 to 400 frames per second frame rate. Habitat-Sim in a single threaded mode runs at a few thousand frames per second, somewhere between 3 to 4,000, depending on the exact scene loaded. And because we own the software stack, we can run multiple instances of the simulator on a single GPU because we can control the memory footprint. And it is fairly easy for us to run 5 instances of a simulator and produce more than 10,000 frames per second for consumption by a neural network downstream. So this is 50 times faster than anything else publicly available. And that is one of the ways in which we're going to scale learning in these simulated environments. But that's not all. We're going to also do distributed learning in these environments. And this is a work that was presented at ICRA this year called Decentralized Distributed BPO. The key idea is that we're going to have to need many, many machines gathering experience in order to learn. And this is not a new idea. This already exists in literature. There have been a number of distributed frameworks for reinforcement learning. But one of the key sort of fundamental assumptions that they tend to make is that simulation is cheap, so that it can be done on a CPU and there can be many, many instances of the simulators. And that neural networks are light and therefore can be run on CPUs again. And both of these assumptions are going to be violated in our case. The kinds of simulated environments that we're going to be using are going to require GPU acceleration. They just do not run fast enough on CPUs. And for the tasks that we are approaching, we're going to need extremely heavy neural networks, which again will require GPU acceleration. And for both these reasons, just out of the box application of classical distributed methods just doesn't work for this case. And so what we did is we designed decentralized distributed PPO, which is a reinforcement learning algorithm for this particular task of point goal navigation. And our basic design paradigm is that there is not just a single instance, but there are multiple workers, each running on a different GPU or a different node. The GPU could be sitting in different nodes that gather experience in parallel, which is followed by an explicit synchronization step of the gradients that they compute at each node. So individually, they are computing gradients with respect to their local copies of parameters, and the gradients are then synchronized in an explicit synchronization step, which is then used to update the parameters, at which point the parameters are also synchronized. Now, this is the scheme that we're going to follow for DDPPU. It's fairly easy to implement, but it's important to ask, how does this scale? We're going to measure this as a speed up with respect to a baseline that only uses on a single GPU, and we're going to extend this to 256 GPUs. Ideal scaling is a straight line, and what we observed is fairly nice near linear scaling. So all the way up to 256 GPUs, we see nearly a 200x speed up with respect to a serial baseline. And that is, again, 2 orders of magnitude speed up that we are observing, in addition to the 2 orders of magnitude from running the individual simulator fast enough, for a cumulative 4 orders of magnitude speed up with respect to all the baselines. And both of these are essential for solving the kinds of tasks that we want to solve. And so now we can answer, okay, so how far does this get us for this task of embodied visual navigation? Well, on the y-axis here is success, and on the x-axis is steps of experience. How many frames did the model consume in learning for this task? And what we notice is that we have scaled this out to 2.5 billion frames of experience. That's billion with a B, 10 to the 9 frames. That's roughly 3 orders of magnitude faster, more than any other studies of this kind that had happened before this work. And we actually noticed fairly nice increase in success. It, of course, starts showing diminishing returns, but it increases all the way to near perfect performance. And this was done with roughly 6 months or 180 days of GPU time on 64 GPUs with a wall clock time of under 3 days. But again, for a final performance on new environments, this is validation performance of 99.9% success. So in a new environment, we can spawn an agent at a random location, give it relative coordinates, and it performs 100% success. And even in terms of path efficiency, we see extremely high, nearly 96-97% path efficiency with respect to the shortest path. That is an impressive result. Here is an example of such an agent. It was spawned at blue, asked to navigate to red. And what we notice is that nearly collision-free, it goes from start to end. Here's an interesting baseline where we simply turned off the vision sensors. So this agent just has GPS and compass sensors enabled. There is no vision, and it's the exact same model, exact same algorithm. The only thing is that the input is different. And we notice the emergence of wall hugging and wall following strategies where the agent goes and immediately slams into a wall and then follows the wall around towards the goal. And it's the emergence of this entirely from exactly the same reward and the same model. Here is a more sophisticated example where we thought this was an exhibition of fairly sophisticated behavior. Here's an agent that is navigating, goes down the hallway, and at this point, something interesting happens. In that we see that the agent has roughly 3 choices up ahead of it. If we look at the floor plan, it can go straight at that blue point, it can turn right, or it can turn left. We know that the GPS and compass sensor is telling it that the goal is located exactly in front of the agent. It is directly in front. It's at some distance away. In fact, if we look at the map, we can tell that the goal is beyond this wall. The depth sensor actually shows that there is a wall directly in front of the agent. There's also a wall to the left. And this information is visible in the depth sensor. And so really the only thing that the agent can do sensibly, the only right answer here is to turn right at that fork. And in fact, that is exactly what the agent does. But it's so subtle that you don't even notice that there was anything that happened here. There was a natural right turn there where the agent then follows the path after that to make its way to the target. Here's another interesting example of backtracking, the emergence of backtracking behavior, where the agent initially overshoots the entry to a door, turns around, follows the wall, comes back, enters the room, and then makes its way to the target. And we found this over and over again. Again, these are new environments where this is happening. Some of these performances are, in certain cases, so good that we can throw up a Turing test, if you will, where there are two options. One of them is the performance of this learned agent, and one of them is just the shortest path on the map. And your goal, if you can tell, is to tell which one is which. So here's option one of identical spawn location, target location, and a particular navigation. Here's option two, the same spawn location, same target location, and a fairly similar navigation. And at this point, I encourage you, before I move on, to make a guess right now whether option one is the learned agent or option two is the learned agent. The right answer is that option one is the learned agent, and option two is just a shortest path on the map, which the agent does not have access to. The agent does not have a map and proceeds entirely from egocentric perception. There are subtle hints. It turns out that these agents like to clip corners, and so they actually touch the corners around, and which doesn't happen with shortest path agents as much. It's a slight tell. At this point, it's a reasonable question to ask, what if I don't have a large GPU cluster? How can I benefit from this sort of scaling? And there are a couple of answers to this. One is to look at that plot again and to point out that there are sharp logarithmic behavior here. And incidentally, 90% of the performance is achieved fairly early at 100 million steps, as opposed to 2.5 billion. And 100 million steps requires less than a day on 8 GPUs, which is much more reasonable to retrain if you had to retrain this. But more importantly, we don't believe that you should have to retrain this. We think of this in the transfer learning paradigm, where this is the ImageNet pre-training equivalent of embodied AI, that you would train navigators on this task, and our pre-trained models are publicly available, and then you would just simply fine-tune this for a particular task, like object goal navigation or room goal navigation, and our models are publicly available. So coming back to that question of how far, so we've seen that these things work well in simulated environments. For a robotics audience, it's a reasonable question. I always get this is, okay, but do these things work just in simulation or also on real robots? And so we've done that experiment as well. This is a project that we recently concluded on SimtoReal Productivity, where we ask whether evaluation in simulation environments are predictive of real-world performance. And in order to conduct these experiments, what we did is we scanned a lab environment using a Matterport camera. The device on the tripod there is a Matterport camera, and we can use it to capture RGPD footage and construct 3D scans of indoor environments. And with that, we can load that into Habitat as a simulator and generate experiences or trajectories in these in that same scanned environments. So as soon as we have this, we basically have paired evaluation. We can conduct exactly the same testing of a model architecture in simulation, run it on a robot. That robot here is Locobot. It's a low-cost robot from researchers at CMU in Fair, Pittsburgh, which we deployed this on. And given this paired evaluation, we can plot what we would call a sim versus real scatter plot. So the x-axis here is performance of a method in simulation. Y-axis is performance in reality. each point on the scatter plot is a particular navigation model that we're testing. And so if this is a good simulator, you should see all points lie roughly on the x equals y line. And for the scatter plot, we can summarize the performance of the simulator through a correlation coefficient, sim versus real correlation coefficient. So this right here is a good simulator because it is producing high correlation between performance in simulation, performance in reality. And this gives us confidence that when we run things in simulation, that they will generalize to reality. And the hope here is that if you have established this confidence, in future, you would not have to run the experiments in reality, because if the simulation settings are good, then you can just run simulation experiments to do model selection. And so this right here, we see reasonably high performance both in simulation and reality. Incidentally, this is not where we started. The simulation setting as used for the Habitat Challenge on 2019 looked a lot like this, where a number of methods looked like they were performing well in simulation, but performing quite poorly, or in fact had a high dynamic range in reality with a low SimtoReal correlation coefficient. And if you want to know the details of this, these are in the paper. But I think one thing that I will just mention here is that we did a lot of engineering work in order to enable these scientific experiments, to the point that we released something called the Habitat PyRobot Bridge, where the sim versus real experiments can be switched by an if command. You can just run exactly the same Python code and just write in config whether you want these experiments to be run in simulation or the robot, and this infrastructure is publicly available to everyone. Okay, so that is where I wanted to go with this particular question of how far we can scale. To summarize the answer to that question, I would say we can get pretty far on point goal navigation with RGBD perception and a GPS and compass sensor. We can get near perfect navigation performance in new simulated environments, completely unseen without access to a map, which I think is pretty surprising. I wouldn't have guessed that before we went into this. Having said that, I think it is important to add a caveat here that it's not far enough. We have not yet gotten far enough. For example, on point goal navigation, if we just take out the localization sensors, performance drops to nearly 50% success, which means that localization sensors are doing a lot of the heavy lifting in this case. So we have not solved that task. And RL scaling, we have not been able to scale RL to a level where it can just solve this task out of the box. On a slightly harder task of object goal navigation, where you're given the name of an object and you have to navigate, performance is even poor. We're seeing sub 10% successes in that case. So there's still a lot of work to be done in this space, but here's the sort of rough summarization of where we are. And I'm mostly done, but before I end the talk, I want to give a couple of pointers to things that are upcoming on the horizon. At CVPR this year, we are organizing a Habitat challenge and an associated workshop called the Embodied AI workshop. The one interesting feature of this challenge is that this is a code upload challenge. We actually ask participants to containerize their code, upload it to our servers, and they are run on completely new environments that the participants have never seen before. And then there is a leaderboard where this is posted. So this is all done through the infrastructure of Eval AI. This year, we are hosting a competition on 2 tasks. One is the point nav task, which is go 5 meters north, 3 meters west relative to start. However, the changes with respect to last year is that there is no localization sensor, no GPS or compass sensor, and the only thing you have access to is an RGBD camera on the robot. There is also increased realism in the challenge setting, in that there is noisy actuation, noisy perception, and a number of other cosmetic changes to the simulation. And the other task that we are hosting this year is the object nav task, where you're given the name of an object, find fireplace, for example, and you have to find an instance of that object. And in this case, we are emphasizing semantics. And so we actually do provide a localization sensor, and there is no sensor noise, there is no actuation noise, because the emphasis is on understanding semantics and not on realism of the robot or the embodied agent. And before I end, I just want to point out that we have a recent work on studying vision and language navigation in these simulated environments. Specifically, vision and language navigation is this task of following instructions, like take a left, go down the hallway, turn into bedroom on the left, stop at the foot of the bed. And this task had been studied largely in a grid or an irregular grid setting, where there was a navigation graph constructed on the floor plan, and the agent essentially navigated on this irregular graph. What we've done is lifted this to a full continuous navigation setting. So you see these green dots on the right are the grid graph or the irregular grid where the navigation would have been constructed. And in our VLN continuous navigation setting, the agent has to do continuous navigation on the floor plan and follow these instructions. And we believe this is a much more realistic version of the task, and can serve as an interesting test bed for evaluating grounded language understanding. What does leave the bedroom mean? You have to understand what room you're in, and what does leaving a room mean. Okay, here are all the references for things that I talked about. The Habitat project is maintained at this website. DDPPO is the paper I talked about. It's appearing at ICRA, appeared at ICRA this year, and the code is publicly available. Pre-trained models are publicly available. And with that, I'll stop and leave you essentially with the message that I think we should really think about embodied AI tasks as a first-class citizen, which I know the robotics community doesn't need a reminder of, but perhaps a reminder to that community would be, it's surprising how far we can get with model-free RL on some of these navigation tasks. And of course, we should augment them next with task-specific understandings. Okay, thank you.